So, last time we were working on page 252, number 62, and we had these two titanium spheres, and the titanium indicates that they're rigid and they're going to bounce off of each other, and they have an elastic collision. And we were supposed to figure out what the mass of the other sphere was, and we got it to be 100 grams. And the part that we didn't do was part B, which is what is the speed of the two-sphere center of mass if the initial speed of each sphere is 2 meters per second. So remember that the spheres are coming towards each other with the same speed. So this was V1I and this was negative V1I. And now we're being told that the magnitude of V1I is 2 meters per second. We know that the mass of 1 was 300 grams and the mass of 2 is 100 grams. Okay. Just to review where we were. And this direction was positive. So when we're talking about the center of mass, we talk about the total momentum, which is going to be equal to the initial momenta of both objects, but that's also equal to the total mass times the velocity of the center of mass. And so we can really just take this part of the equation and solve it for V center of mass. So what's my formula for momentum? mv. Okay, so I'm going to have m1 v1i, bless you, plus m2 v2i is going to be m1 plus m2, because that's what capital M is, times v center of mass. And we are solving for v center of mass. So we know that V2I is negative V1I. So I can do a little algebra here. And my center of mass velocity is then going to be m1 minus m2 over m1 plus m2 times v1i. You okay? Gianni, are you okay? Okay. She was blowing her nose for a really long time. I just wanted to make sure she was all right. This way, write down what you're writing down. Okay, and then we can substitute everything in. So we've got 300 minus 100 grams. Why can I leave them as grams? Right, because they're just going to cancel out, plus 100 grams. And I know that V1I is 2 meters per second. So that's going to give me what? Zoe says 1 meter per second. Is she right? Okay. This is going to give us 200 divided by 400. So that's going to give us 1/2 times the 2 from the meters per second. Okay. We good? All right. So the next thing that we want to talk about are collisions in 2 dimensions. And so remember that momentum is a vector, which means that it has components. And just as we applied Newton's second law to different directions separately, we can do the same thing with conservation of momentum. So for elastic collisions, I can say that I've got px initial is equal to px final, py initial is equal to py final, and these again are total momenta. And I can still say that k initial is equal to k final. But remember that you have to use the speeds. So that v1i is going to be the square root of v1xi squared plus v1 yi squared. That when you are using the kinetic energy formula, you cannot conserve kinetic energy separately in each direction. You need to use the speed of the object. So when you're substituting in for your initial kinetic energy and you want to have v1i, for when you're figuring out the initial kinetic energy of object 1, you need to combine the x velocity and the y velocity using the magnitude formula. Okay? I can't stress enough how important that is. And I guarantee one of you will try to conserve the kinetic energy separately in each direction. Not taking bets, but it'll be somebody. Okay? So, we can also write a similar thing for inelastic collisions, but here only the momentum is going to be conserved. But we can still conserve it separately in each direction. Because no matter what kind of a collision I have, my momentum is conserved. All right, we good? We got it? Oh, pardon me? Greek Slovakia. All right, we good? All right, then let us do sample problem 21. Okay, if somebody would read it for us, please. Yep. Okay. So, I find that when we're dealing with 2 dimensions, it's best to put everything on one axis. Okay? So, I'm going to have my ball B here that's initially at rest. And I've got ball A here that's coming in with some velocity, VAI. Okay, and this is my before. Okay. And we are told that afterwards, ball A is going to go off at a 30-degree angle with some final velocity, VAF. So my first question to you is, what's going to happen to ball B? Yup. Well, you should have some idea of where it's going to move. Well, what do you think, Casey? Totally downward? Angle downward? Okay, Zoe, what were you going to say? Well, why do you want it to go down? I don't have to even out velocities. Velocity is not conserved. Nope. Even out the momentum. So let's back up for a minute, because everybody said a lot of important stuff. What direction is the total momentum in before the collision? Positive what? X. So after the collision, what direction does the total momentum have to be in? Positive X. So if I've got some momentum in the Y direction, which we have from object MA, you're absolutely right that object MB has to be going in the opposite direction in Y. It's got to be going in the negative Y direction. But it's so that the momenta in the Y directions will cancel. So it's going to have some velocity that we don't know, VBF. Exactly. It doesn't have to be the same angle because they're different masses. And it's the angle that's going to determine that. And I think, we can just call it theta. Okay. If they did have the same mass, then yeah, they may very well go off at the same angle if they had the same speed. Okay. So we'll have to figure that out. All right. So everybody got the picture? Everybody understands what's going to happen here? Okay. So part A just wants us to write down the equations that we're going to use. All right. We could actually do this. Okay. So because this is a collision in 2 dimensions, we don't know whether it's elastic or inelastic. But I do know that for every collision, what is conserved? Momentum. Okay, so I can certainly say that PXI or PX initial has to be equal to PXF, and that PY initial has to be equal to PY final. And that's where our 2 equations are going to come from. Okay. And then it's pretty straightforward. We're just going to write down the momentum of each object. So I've got MA, VAI, plus MB, VBI. In this case, because they're all in the X direction. But when I go into final, it's going to be MA, VAX, F, plus MB, VBXF. Things start to get a little crazy. Okay, so I know that term can go away because my ball B is initially at rest. That's just a number. How might I write VAXF in such a way that it's not gonna, yes, look so utterly disgusting. Go ahead, Maddie. Okay, VAF cosine 30. And I can write a similar thing for BXF. It can be BF, but now it's going to be cosine whatever theta is. And so this is really half of our answer for part A. Of course, we have to acknowledge that we have two unknowns. What are my two unknowns? VB, at this point, it's VBF and theta are my unknowns. Okay. And so now I'm going to need another equation so I can take my momentum in the y direction and write that. So I'm going to have PYI is equal to PYF. And what's PYI? 0. And then PYF, I get my wacky thing here, MA times VAYF plus MB times VBYF. And then I know we've already established that my VBY final has to be negative, right? So I'm going to get rid of my vector symbols and put my negative sign in there. And then that can just be VBF sine theta. And I can bring things over to the other side. So I've got MB VBF sine theta is MA VAF sine 30 degrees. And now I have two equations and two unknowns. Okay. We good? All right. So I'm going to take this and copy it. I don't really want to do that. Go away. Go away. All right. And we got rid of the highlighting, which was everything that I wanted. So we've got two unknowns, the VBF and the theta. And we all know that solving for theta is always a bit of a tricky mess. okay? Especially because I have sine theta here and cosine theta here. And hopefully in your lives you have realized that what I really want to do is somehow turn that into a what? Lovely, it would be, but I certainly don't want to take the cosine inverse of the sine of the angle. So what do I want to turn that into? Yes, and what trig function? A tangent. Because that would make my life easier. If I could somehow divide one thing by the other and end up with tangent theta, I can solve for that on my calculator. Okay. So again, because I am an omniscient and omnipotent narrator, which means I know all and can do anything I want, I'm going to solve this for MB VBF. It's the second equation. The easy equation. No, the simpler equation. We won't put value judgment. Well, it's still value judgment, but I don't think anybody would argue that it's the simpler equation. Okay. Now, I do in fact know what MB is, but I know that I've got MB VBF in my other equation. So why like divide by something that it's just going to cancel out later? Okay. So now, that was not really what I wanted to have happen. We're going to take this equation okay. So take a mo and write it down. And remember that everything up here is a number. So that's just a number. It doesn't look like a number, but it's a number because I know MA, I know VAF, and I know what the sine of 30 is, or at least I know my calculator does. I was confused it with the sine of 60. But, okay. So I'm going to take this whole thing and substitute it into here. Huh. So I'm going to have MA VAI number, right? Because I know all of that. MA VAF cosine 30 degrees, another number. And then I'm going to sub in. So I'm going to have MA VAF sine 30 degrees, a number, divided by sine theta times cosine theta. Except that it's not. Because what's tangent theta? Yeah. Yeah, so what's the big deal? It's 1 over tangent. Okay. So we can do a bunch of stuff here, right? I can take this and bring it over to the other side. So I've got MA VAI minus MA VAF cosine 30. That's going to be MA VAF sine 30 divided by tangent theta. Do whatever you want. This isn't actually the way I usually do it, but I'm going to write it this way anyway. So I'm going to cross multiply and divide and all that stuff that you know how to do because you're in AP Physics. And divide that by MA VAI minus MA VAF cosine 30 degrees. You plug it into your calculator, and what are we going to get? But you can do it. You survived it once. We haven't even gotten to the damping thing yet. That's the when we do damp simple harmonic motion, that is the algebra to end all algebra. What? Simple harmonic motion is something that happens over and over again. Yes, a swing is an example of simple harmonic motion because anything that has a period, yes, has simple harmonic motion. What'd you get, Casey? Did you take the number 1? Did you take the inverse tangent? Number 2, are you in degree mode? Just saying. 32.9. What'd you get, Priya? Okay. That's 2. I have 33, but I don't know why I mysteriously threw away a sig fig, so we'll call it 32. Oh, see, then it is. Because people know how to round better than that. Please. Not spent my life slaving over you to have you round so foolishly. Please. So now we're not done because you still need to tell me what VBF is. So substitute back into some formula and tell me what VBF is. You do have 3 sig figs. Yeah. So let's see what other people got. Okay, Elisa confirms. All right. So a lot of algebra, but doable. You just got to slow down and remember what you know. Okay. I'm going to end here because the next thing we're going to do is the rocket problem, and I need to do that all in a piece. We've got, I think, 55 minutes tomorrow, and that should be enough to do it. All right. And then that ends chapter 9. So as we discussed, expect the chapter 9 part 2 homework to be due, like Monday. Okay. And then the chapter 9 test will be coming. If we have time tomorrow, we can discuss a date. All right.